Today we will speak about convergence of random sequences. And the question is, think about we have a sequence of random variables, x indexed by n, and then we ask, okay, does this sequence have a limit? And then we might think that yes, maybe there's a limit in some sense, but what is the sense that would make things sensible here? Thing is that there are many choices here. This convergence could take place in many different ways. The strongest of all is to fix the context, let's recall that as always, we assume that we are looking at a certain probability space here with some probability measure on a sigma algebra, and then we are looking at a setting where xn and x are defined on omega. And the basic thing would be to require that because xn is a function from omega to the real line, let's assume that xn and x, they are maps from omega to the real line. If you don't like real numbers, you can replace this with your favorite topological space, but let's fix real line for now to be concrete. So the basic thing is that, okay, these are functions. So we could think that, okay, what does it mean for a sequence of functions to converge to a limit? Well, the most basic thing is that, okay, we say that at every point where we evaluate this function, we require that there's a limit in this sense. Okay. We remember already that where these are defined, so let's take these away. And let's focus on this. So this is one definition, and that has a name. It's called pointwise convergence. It is the pointwise convergence of functions that you might probably have seen in many other courses. This is rather convenient. If you can prove pointwise convergence of functions, then you might derive lots of consequences that you might like. But actually, this is too strong for many practical purposes, so that's why it's actually rare. In applications, it's not very common that you could prove convergence for every point omega. That is kind of the cornerstone of ergodic theory, where several great minds worked on, let's say, they worked on mechanical systems of mechanics, dynamical systems, iterated functions, and they actually learned, let's say, maybe Birkhoff was one of the biggest influencers there. They discovered that actually in many cases, pointwise convergence is not possible to do, but instead, what you might be able to do is to prove that, or let's actually say that what you might be able to prove is to say that the convergence is almost sure. And this is what is called almost sure convergence. And what it means is that by the definition of this thing is that the probability of the event, so we look at the set of points in omega for which this limit of xn exists and equals x of omega. So the probability of the good event where the convergence is true is assumed to be 1. That's what is defined as almost sure convergence. And a special notion to make is that implicitly we assume that this is a collection of omegas, so we assume also that this is an event, so it's a measurable set, these omegas. On the other hand, we already know that, or let's say, whenever we say that something occurs with probability 1, so then we are discussing some event for which we say that it has probability 1. But implicitly, we always assume also that the event that we are discussing is a measurable event or measurable set. In this case, we don't need to require it because we actually remember that because xn, these are measurable functions. So then the limit is also measurable whenever it exists. So here we don't need to explicitly actually think about anything more than just say that this event is a proper event and it has probability 1. And these are the two kind of basic things. And actually, related about the first one, so actually nobody speaks of it in probability. So what I would like to do is that I would like to actually ignore this part 1 completely. And actually, that's what everybody does. Why is it possible to ignore this case as well? Always. Think about the setting. Assume that let's make one remark first. First remark is that if xn converges pointwise to x, then there's an implication that then xn converges almost surely to x. That's rather trivial, isn't it? If there's a pointwise convergence, then we look at this set. Let's call it omega 0. Let's call omega 0 the collection of those omega for which this convergence is true. Assume that we have a pointwise convergence. If this is true, then what happens then? Omega 0 happens to be omega. Yeah. Then probability of omega 0 is equal to probability of omega itself. And the probability of the full set is 1. So then we know that the probability of the event that we have convergence is actually, that probability is 1. So this is why we see that this, we can say that this is trivial implication, of course, in this way. What about the other direction? If we do have almost sure convergence, so what about the pointwise convergence? Well, I just spoke about ergodic theory and Birkhoff and stuff. So in many cases, you can prove almost sure convergence, but you cannot prove pointwise. So the other direction is not true mathematically, but I would like to say it's morally true, or morally it's close enough so that we could ignore this definition 1 completely. And okay, what would I mean by that? Let me clarify. Assume Let's assume that we have almost sure convergence to some random variable x in this way. What then? Then we know that probability of omega 0 is 1. Yes, that's the definition of omega 0 and then the definition here. Then think about any other event that you might study. So let A be any event that you would like to understand. Okay, so we'd like to study, let's say, the probability of event A. So if we want to calculate what's the probability of event A, so we can split it so that we say event A intersection omega 0. And then because we have a disjoint union, we could say A intersection omega 0 complement. Then what happens about this complement? This has probability 0, so and this is a smaller set. So some set which is less smaller than an event of probability 0. So that's why this event must have probability 0 as well. So actually, we know that for any event A here, we know that when we calculate the probability of A, we can calculate it the same way as we took A intersection of omega 0. Yeah. So essentially, we could assume that this condition omega 0 is already valid, and then we calculate the probability of event A. In practice, this is what we always do when we calculate probabilities. What about take any non-negative random variable? So let's call it, let's take some non-negative random variable z, and let's calculate the expectation of z. Again, we can split that. Okay, we say z is the z times the indicator of omega 0 plus z times the indicator of omega 0 complement. Because either the indicator is 1 here, so then this one is 0, or this one is 0 and this one is 1. So that equality holds always. And that's why we can write this as the expectation z times indicator omega 0 plus expectation z times indicator omega 0 complement. And if you look at this random variable here, this omega 0 complement has probability 0. So then this is 0 on an event of probability 1. So actually, if you recall carefully the definition of expectation and the definition of Lebesgue integral. So if you integrate something which is 0 almost surely, then the integral is 0. So there's nothing there. And actually, what we conclude here is that whenever you calculate any expectation of any random variable, you could calculate it by taking the expectation and then you take indicator with this event of probability 1. And this is why, again, when calculating expectations, we can ignore the complement of this omega 0. So morally, we can ignore what happens in this outside this event. And that's why we might actually even do so that we define a new probability space, omega 0, f0, p0, where we say that omega 0 is, well, omega 0 is this omega 0 where things hold for this convergence. F0 could be the event, the sigma algebra with events with intersected with this omega 0. So this could be the sigma algebra where you intersect a intersection omega 0 and with a being in F. And then P could be the restriction. So you calculate probabilities only for this sigma algebra here. And now with this kind of construction here, we have a new probability space where probabilities and expectations are the same as in the original probability space. But in this restricted space, we have this pointwise convergence. So if we assume that we have almost sure convergence, we know that there's an event of probability 1 where this convergence is true, then morally we can restrict out the probability space to this omega 0, and then we can, if we need it, we could redefine things and assume that actually everything holds pointwise. So that's the reason why in practice, if you needed pointwise convergence, so we know that there's no implication, but by redefining your space properly and restricting a bit, so then you could actually forget about this. And that's why the story is that the relevant concept of convergence in probability theory, let's take this out and let's actually remove this, because having seen it once and knowing that it's actually not very useful in statistics and probability, so we don't define it anymore. But we know the connection.